Okay, in the last lecture, so we have discussed about the basics of behavioral modeling, and then we have discussed some examples, AOI gate and OR invert gate with and without tri-state buffer. Then we have discussed 2 by 1 multiplexer and 4 by 1 multiplexer. But in these examples, we have used continuous assignment. So, we know that in the basics of VLSI Verilog, so we have discussed about the two types of assignments. One is continuous time, another is procedural assignment. Okay. So, one of the very important feature of this behavioral modeling is it enables these procedural assignments by means of a procedural block. Okay. So, today we will discuss about how to implement the same multiplexers using procedural assignments. Okay. So, behavioral modeling using procedural block. Okay. So, what is this procedural block? This contains assignments, this contains loops, the conditional statements, such as if then else. This is similar to the C language, and we can have some timing control also. So, this is one of the powerful block in behavioral modeling. So, this allows the assignments, loops, conditional statements, timing control. Again in the assignments, we have two types of the procedural assignments, which we have discussed in the basics of Verilog. This can be blocking or non-blocking. So, in blocking normally we will use this operator, in non-blocking we will use this operator. So, in case of blocking, as the name implies, so the execution of one statement blocks the execution of the other statement. Okay. Whereas, in case of non-blocking, we can execute all the statements simultaneously. Okay. So, we will use in these assignments, that is in the procedural assignment. So, one of the important feature is the target output must be register type. So, we know that we have different types of the data types. So, in that wire, register. So, normally this wire will be used in continuous assignments, whereas this register will be used in procedural assignments. Okay. If you have a look into the differences between the wire and register data types, so this wire cannot store the data without being driven. whereas the register can store the data or value until a new value is assigned. This is one of the important difference between the wire and register. Okay. If you take say for example, so there is some gate whose output, if I connect through this tri-state buffer to some other gate, if we define this as wire, okay. Suppose initially if it holds a value of 1, so when this control signal of this buffer is 0, okay. So the output of this buffer is driving this wire, so that as long as this control signal is 0, so this output of this buffer is 1. Okay. Suppose if one of the input is 1 here, this is 1. So, control signal is 1 or 0, it depends upon the logic. Okay. If I use the negative logic, control signal is 0, output is equal to input, control signal is 1, output will enter into the tri-state buffer. Suppose if I make this C is equal to 1, the output will goes into tri-state buffer, this will not hold the previous value 1. Okay. So, this can store the values only, so when it is driven. Okay. So, it cannot store the value without being driven. Instead of wire, if I define using register, even if you make this C is equal to 1, the value of the register remains the previous value 1, even this is floating. So, if this C is equal to 1, then it will enter into the high impedance state, which is almost like floating. So, here again this register will store the previous value, this is something like the register, it will hold the previous value. Okay, that is the difference. So, register can store the value until a new value is assigned, whereas the wire cannot store the value without being driven. And the second difference between the wire and register is, wire is normally used in the LHS of the only legal data type in the LHS of assign keyword in case of continuous assignment. Okay. If you have something like assign, you can have some y is equal to x exclusive y, x exclusive say a exclusive b. Okay. Here this can be wire. In case of assign statement, the LHS of this assign keyword is a wire, this is only legal type, whereas register is the only legal data type in the LHS of always. Normally, this always will be used in the procedural statements, block after either this operator or this operator. So, example is if I write always at the rate a or b, y is equal to a exclusive or b. Or you can have y, this is non-blocking, this is non-blocking a exclusive or b. So, in this target output y must be a register, whereas here this is wire. Okay. So, in always LHS should be register, in assign LHS should be a wire. Okay. This is another difference. So, wire is normally used for modeling combinational circuits. Whereas resistor can be used to model both combinational and sequential circuits. So, normally in case of combinational circuits we will use blocking statements, means we will use the operator this, whereas in sequential circuit normally we will use non blocking operator. So, these are the main differences between the wires and resistors. Okay. Now, in the last lecture we have written the Verilog code for the multiplexer using wire concept, that is continuous assignment. Now, we will see how we can write the Verilog code if you use the procedural block or procedural assignment using always keyword. So, this is 2 by 1 mux. You call this signal as select signal S, and 2 inputs you call as A, B, output is Y. So, we know that the operation is S is 0, output should be A. If I connect to 0 and this is connected to 1, S is 1, output should be B. Okay. So, module 2 by 1 mux, output is Y, inputs are A, B and selection signal. Out Y, inputs A, B and S. And because we are going to use procedural assignments, so the target output must be register. So, you have to define register Y. So, these two together can be written in a single statement. You can use output followed by register then Y. This is also possible. Okay. Then you have to write always at the rate followed by there is some conditional statement. So, what is the condition for the output to change? Either A changes, B changes or S changes. You can write or also here. Okay, instead of that we can write the bracket also. Here you can write this statement as always at A or B or S. Instead of using this or operator, you can use or you can simply use comma. Okay. Here I am using comma. So, in the latest versions and all, comma will be used. In the older versions, or is going to be used. Okay. So, always at A, B, C, and another important thing is here, after always there will be no semicolon. If S output Y is equal to B, else output y is equal to A, end module. This is called conditional statements. As I have told, procedural block, this entire thing is procedural block, this is procedural block. This will consisting of, there will be always keyword followed by some condition followed by the procedural statements. These are called procedural statements. So, these procedural statements can contain the conditional structure, or it can have loop. Okay. So, we will discuss in the coming classes the examples on the loops, or it can have timing control. Okay. So, here this statement if else S, if this S is true, then this will be executed, true in the sense 1. So, in this, if S is equal to 1, that is true. So, then this particular statement is executed, otherwise else this statement is executed. Okay. So, this is the format of if else structure. This structure is exactly similar to that of C language. Okay. So, this is the Verilog code using procedural assignment, and we have used blocking assignment because this is a combinational circuit. Normally, in case of sequential circuit, we will use non-blocking. Okay. Now, we will take another example of 4/1 multiplexer. Here, we will introduce another concept called case. So, we know that 4/1 multiplexer will have 4 inputs. Let us call the inputs as A, B, C, D. This is connected to 0, 1, 2, 3 inputs, and only one output. So, this target output you have to use as a register data type, and here this is S1, S0, 2 selections will be there. So, the operation is S1, S0, output Y, 0, 0, it should be A, 0, 1 B, 1, 0 C, 1, 1 D. This is the truth table of 4/1 multiplexer. Now, we are going to write this Verilog code using case statement. This case will act as a multi-way conditional statement, multi-way conditional branch structure. If else is single way. Now, if you want to have the multiple, here you have only S can be 0 or 1. Okay, only one possibility is there, whereas here now we have 2 selection signals. So, there are 4 possibilities. So, this is called multi-way conditional branch structure. Okay. So, module 4/1 mux, output is Y, inputs are A, B, C, D, S1, S0. Output, I will include register also, register Y. So, these two are 2 keywords separated by tab. Then input A, B, C, D, and another input is, this is vector, we can call this as a 1:0 S. This is S1, S0. Then always we are using procedural statement at either A changes, B changes, C changes, D changes, S1, S0. Case S. Here this S is now 2 bit, this S is 2 bit, whereas in the previous example this S is 1 bit. Then what are the 4 possible values of these 2 bits? 2 bit, this is the representation of the numbers in Verilog. This can be 0 0 to binary, this stands for 2 bit, B stands for binary, 0 1 colon 2B 1 0 colon 2B 1 1 colon. So, if this is 0 0, what is output y? Y is equal to A. So, 0 means 0 input is connected to A, semicolon. Here output y is equal to B, semicolon, output y is equal to C, semicolon, y is equal to D, semicolon, end case, end module. Okay. So, this is how we can use a multi-way conditional branch structure by using case statement. Okay. Now, we will discuss a 2 to 4 decoder, another example 2 to 4 decoder using the behavioral model and that too the procedural assignment. Okay. So, this we have already discussed while discussing about the gate level. So, in gate level we have discussed about the internal circuitry also, whereas here now we will use only the block diagram approach. We do not bother about the internal circuitry of this 2 by 4 decoder. We are just now interested only in the function of this circuit. So, 2 by 4 decoder, as the name implies, 2 inputs will be there. This is A B, you call this as MSB and this is LSB, and 4 outputs will be there. This you connect to 0, 1, 2, 3, you call W, X, Y, Z. So, I am not considering the enable signal for this decoder. And what is the operation? We are interested here in behavioral modeling only the operation. So, A, B, W, X, Y, Z, this is 0, 0, 0 output will be selected. If I use the positive logic, selected means 1, not selected means 0. So, 1 W is selected, these are all not selected, 0, 1, X is selected because X is connected to 1 input, 1, 0, Y is selected, 1, 1, Z is selected. This is the truth table of 2 to 4 decoder without enable signal and uses positive logic. So, if I know this operation, it is enough to write the Verilog code. Whereas, in case of gate level or structural modeling, we should know the internal circuitry of this circuit, this block. Module 2 by 4 decoder, outputs are W, X, Y, Z, inputs are A, B. Output and all the target outputs we have to declare as a register data type. So, I am using 2 keywords, output is one, another is register. So, W, X, Y, Z, input A, B. Here also I will use the case statement because here I have 4 possibilities. Always at the rate either A changes or B changes. Here we are going to use case. Two bit binary 0 0 output will be W is equal to 1 comma x is equal to 0, y is equal to 0, z is equal to 0. They are all commas, not semicolons. Finally, here we have semicolon. 2b 0 1, this is colon, w is equal to 0 comma, x is equal to 1 comma, y is equal to 0 comma, z is equal to 0 semicolon. Similarly, 2b 1 0, w is equal to 0, x is equal to 0, y is equal to 1, z is equal to 0. 2b 1 1, w is equal to 0, x is equal to 0, y is equal to 0, z is equal to 1 semicolon, end case, end module. This is about the 2 to 4 decoder using case statement. Okay. Similarly, you can have comparator also. Another example is a 4-bit comparator. This also we have discussed in gate level modeling. So, in case of gate level modeling, 4-bit comparator is very complicated circuit. Okay. So, the Verilog code takes lot of statements, okay. Whereas here we can very much simplified the Verilog code correspond to 4-bit comparator. Here basically we are taking two 4-bit numbers A and B. This is A3, A2, A1, A0. This is MSB and this is LSB. B is B3, B2, B1, B0. If A is equal to B, we are taking 3 outputs. Equality is 1, greater than is 0, less than is 0. Okay. If equal, equality output will be 1. Okay. Similarly, if A is greater than B, equality is 0, greater than is 1, less than is 0. If A is less than B, equality is 0, greater than is 0, less than is 1. So, we have two 4-bit input numbers and outputs are, we have 3 outcomes. One is equality, another is greater and next one is lesser. Okay. Here also we can use this always statement and case statements. Module, 4-bit comparator, you can use the output as E, G, L, inputs are A, B. Here I read single bit only, later I am going to define this. Output as well as register E, comma, G, comma, L. Input, this is vector 3:0 A, comma, B. Then always at A, comma, B, if A or B changes. So, this A stands for if any of the bit changes A3, A2, A1, A0. Similarly, B means any of the bits B3, B2, B1, B0 changes. Okay. If A is greater than B, then E is equal to 0, G is equal to 0, L is equal to 0, G is equal to 1, and last semicolon. Else if A is less than B, this A less than or A greater than, this will take the 4 bit as a whole, okay, instead of taking as individual bits. So, E is equal to 0, G is equal to 0, L is equal to 1. Else the only possibility is if these two are false, then A is equal to B, E is equal to 1, G is equal to 0, L is equal to 0, end module. So, this is very much simplified, and if you take this structural level or gate level modeling, so it will contains many statements and the Verilog code is very much complicated. Okay. So, there are few combinational circuits. Now, we can use the sequential circuits also. If I use another example of a D flip flop sequential circuit. Here also we need only the overall operation of the D flip flop. We do not need the internal circuitry, which we have discussed in the earlier classes to describe the structural or gate level modeling. So, this is D flip flop with D input, Q output, Q bar output of course, and there is a clock. This can be either level triggered or edge triggered. If I assume that this is positive edge triggered, as I have told here, if there is no bubble, we will use this symbol for positive edge triggered, this symbol for negative edge triggered. Okay. Whereas D flip flop can be level triggered also, there is no problem with race around in case of D flip flop, because in D between J and K we will be having inverter. So, J K can be 0 1 or 1 0. So, in 0 1 combination of J K and 1 0 combination of J K, there is no race around condition. The race around condition occurs only when J is equal to K is equal to 1, whereas in D flip flop that condition never occurs. Okay. So, we have seen that this output Q is equal to D simply. So, at every positive edge, okay, so this output Q becomes simply D. Whereas at other 3 portions of the clock, which is negative edge, positive level, negative level, the output remains in the previous state. Okay. At only positive level, whatever the input D is transferred to the output. Okay. So, module, I will give the name as D flip flop, DFF, because I am going to instantiate this in the later examples. So, there is 2 inputs and 1 output Q, D, clock, output, and also we have to declare as a registered data type Q, input, D comma clock. Then always at, this is positive edge, the keyword is pass edge of which signal? Clock. So, we have to assign D is equal to Q. Here we are going to use the non-blocking statement. Okay. Then end module. Now, finally, I want to construct a counter. So, for that we require T flip flops. So, you see the code correspond to D flip flop. Now, using this D flip flop, I will first construct the T flip flop then using 4 such T flip flops I will implement a 4-bit ripple counter. Okay. Now, I want to implement a T flip flop. By instantiating the D flip flop. Means how to implement a T flip flop using D flip flop. So, given a T flip flop or given a D flip flop, this D flip flop is given as it is, this is D Q bar and with clock. So, I have to use some conversion logic here. With input is T overall, so output should be D. This can be a function of Q also. This combinational logic is basically a function of T and Q. You can use lowercase letter, it is up to you. Now, overall we will be having this clock is of course common, this clock will be clock for even this T flip flop also. So, this is the clock CLK. Overall now this will be your T flip flop. Inside this block we have T flip flop, D flip flop and a conversion logic. Okay. So, finally, this is the output of T flip flop also. Okay. So, for the overall T flip flop, we have one input T, another input clock, output is Q. But inside this we have a D flip flop, we can instantiate this D flip flop, but only thing is we require what is this conversion logic. Okay. To obtain this conversion logic, we should know these excitation tables of D flip flop and T flip flop. So, these excitation tables can be derived from the truth tables. So, if I take the D flip flop, what is the truth table? D Qn present state, next state is Qn plus 1, 0 regardless of the previous state, Qn plus 1 is 0, 0 even previous state is 1, this is 0, simply D. If D is 1 regardless of the previous state, this will be 1. Then excitation table is one of the important table which will be used for deriving the conversion logics as well as design of synchronous counters. So, this truth table will give the present state as a function of the present input and previous output, because the flip flop is a sequential circuit in which output not only depends upon the present inputs, but also on the past outputs. Okay. Excitation table on the other hand, so this will determine the input required for a given change of state. So, input will be a change of state Qn to Qn plus 1. So, there are 4 possible changes. I want to retain in this 0 state only. Before application of the clock, output was in 0. After the application of the clock also I want to retain in the 0 state only. So, what is the D required? Or before application 0, after application of the clock I want to change the state as 1. What is the D required? Or before the application of the clock, this is 1. After application of the clock, I want the state as 0. What is the D required? Similarly, I want to retain the state as 1. What is the D required? This you can easily obtain from here. You see here 0 to 0 transition is here. So, the corresponding input is D is 0. So, this D is 0. 0 to 1 transition is here. The corresponding input is 1. So, this is 1. So, 1 to 0 is transition here 1 to 0. So, the corresponding input required is 0. 1 to 1 is this is 1. So, this is 1 to 1 is here, the input required is 1. So, this is the simply excitation table of D flip flop. Similarly, if I consider T flip flop, the truth table is T Qn plus 1, 0, simply Qn plus 1 becomes Qn. So, this 0 is transferred, 1 is transferred. T is 1 toggles, previous state if it is 0 1, if it becomes 1 it is 0, this is complement of Qn. So, what is excitation table? This is truth table, excitation table of T flip flop is for a given change of state, what is the input T required? 0 to 0, this 0 to 0, input is 0, 0 to 1 is here 1, 1 to 0 is here 1, 1 to 1 is here 0. So, using these two excitation table, I can convert any flip flop into any other flip flop. Okay. So, there are total 12 combinations of these conversions. There are 4 flip flops SR, JK, T. Okay. So, we can convert SR to JK, SR to T, SR to D. Similarly, if I take JK, JK to SR, JK to T, JK to D. Similarly, if I take T, T to SR, JK, D, D to JK, SR, T. So, totally we have 12 different conversions, okay, but the procedure is same. Conversion of D flip flop into T flip flop. So, you have to express D as a function of T. So, you take Qn plus 1 and you take T, this is D, this is given flip flop you have to take at the extreme end and this is required flip flop. This is 0 to 0, 0 to 1, 1 to 0, 1 to 1. So, what is T and what is D? T is 0 1 1 0, 0 1 1 0, whereas D is 0 1 0 1. So, I have to express D as a function of T and Qn. This Qn plus I am writing to just fill these entries of D and T, but after that you can neglect this. I have to basically express this D as a function of this T and Qn. So, what is the expression? So, wherever D is equal to 1, you read the corresponding terms. So, D is equal to 1 if Qn is equal to 0 and T is equal to 1, or here also 1, Qn is 1 and T is 0. So, what is the Boolean expression for D? Therefore, so this is Qn is equal to 0, T is equal to 0 is nothing but Qn bar T, R is plus, and this Qn is 1 equal to means Qn T bar. This is exclusive OR between T and Qn. So, the conversion logic that is required here, this conversion logic is basically exclusive OR gate. So, this is D flip flop. Here I am writing the lowercase letters, because normally in Verilog code we will write lowercase letters. So, this D nothing but exclusive OR, this is T, this is T, this is Qn. And this clock is of course common to both. This is the overall circuit diagram of T flip flop using D flip flop. This is conversion logic. Now, I can instantiate this T flip flop to write the code for the T flip flops. So, the Verilog code for the T flip flop is module. I am using T flip flop is the name. So, what are the inputs and outputs? Input is T clock, output is Q. This is overall output of the T flip flop. Q comma T comma clock. Output as well as register Q, input T comma clock. Now, here this bit is, if I call as this as dt, this you have to define as a wire, because this is combinational circuit. Okay. So, here we have to define this dt as a wire. Then how to obtain dt from T and Q? This is continuous assignment. Assign D is equal to T exclusive or Q. This is continuous assignment. Once if I obtain this dt, then I can instantiate D flip flop. So, D flip flop, whatever the name that is given in the this one, you have to take here as it is D flip flop, and I will give the overall this one as some T flip flop. This name you have to use if you want to instantiate this D flip flop. So, what are the outputs and inputs of this D flip flop? dt is the input, output is Q, inputs are the order in which I have given this input and outputs. Order is Q, D, clock. If I follow the same order, D, in place of D we have dt, CLK, end module. In fact, here another important thing is here out this no need of this register here, because in this D flip flop we have already defined that as a register. Here we have already defined register, so no need to define here. This is about conversion of D flip flop into T flip flop. Okay. So, using this T flip flop we can construct the counters, okay, that we will discuss in the next lecture. Thank you.